The truth lies somewhere in the middle of the generated tokens by Sophie L. Wang, Philip Isola, and Brian Chung from MIT. If you are an ML engineer extracting text embeddings from autoregressive models, you are probably leaving massive amounts of semantic information on the table.
Oh, absolutely.
This paper proves that semantic information in a large language model isn't localized to a single position. It is distributed temporally across the generated tokens.
Right.
By mean pooling the hidden states across the generated outputs, rather than just grabbing the last token, you get significantly richer, more accurate semantic representations.
And the MIT researchers validated this rigorously. They measured the debiased centered kernel alignment, which we'll call CKA, between the LLM's internal representations and established reference spaces across multiple domains.
Like vision and proteins, right?
Exactly. They used Dino V2 for vision, ESM3 for proteins, and gold standard solutions for reasoning tasks like Math 500. And in every single test, pooling the generated tokens outperformed the best individual token. The knowledge isn't in one spot, it's in the aggregate.
So that is your 60-second TLDR. But now that we have the short-form summary out of the way for the clip, welcome to another Breakdown on AI paper podcast.
Nice to be here.
We summarize AI and tech papers for the engineers actually building this stuff. And our mission today is to unpack why this research completely upends how we think about vector embeddings. Because, let's be honest, if you proposed meme pooling autoregressive hidden states a year ago, you would have been laughed out of the room.
Oh, yeah. It definitely violated the established conventional wisdom. People thought you were crazy to try it.
Right.
To understand why it's such a breakthrough, we really have to look at why the industry adopted the last token approach in the first place.
Which comes down to architecture, doesn't it?
Exactly, yeah.
Yeah.
If you are using a bidirectional encoder, like the classic BERT models, every token is computed under a shared context.
They all look at each other simultaneously.
Right, because the context is universal across the sequence. It's mathematically intuitive to mean pool them. Or you can just grab a dedicated classification token to get a solid embedding.
But autoregressive models, the decoder-only architectures like GPT-4, Llama, or Qwen, they don't have that luxury. They rely on causal masking.
Yes.
Token number 5 can only see tokens 1 through 4. It is entirely blind to token 6.
Which means every single token in the sequence is computed under a different expanding context window.
Right, it's always shifting.
Yeah, so the traditional assumption was that if you average these hidden states together, you are mixing vectors that were computed under entirely unequal contexts.
Like comparing apples and oranges, basically.
Exactly. The field assumed that averaging them would just result in a muddy, incoherent representation. So engineers just defaulted to grabbing the final token.
They just assumed it contained the ultimate, fully contextualized state of the model.
Yeah, that was the logic.
It's like, imagine trying to understand a complex murder mystery by only reading the very last page of the book.
It sounds ridiculous, right?
Very much so. Sure, you find out who the killer is, you get the final output. But you completely lose the incredibly rich, accumulating context of all the clues, the false leads, and the tension that actually led you there.
That's a great way to put it.
If you only look at the final token, you're just getting the conclusion. Mean pooling, as this paper proves, is like taking the aggregate understanding of having read the whole book, chapter by chapter.
And that analogy actually captures the mechanical reality of what's happening inside the neural network.
Really?
Yeah, and it challenges a much broader assumption, too. For a while now, the consensus has been that generative language models just aren't naturally optimized to make their hidden states useful as static embeddings.
Right. People thought you had to train a model specifically for that.
Exactly. The thought was, if you want a generative model to produce good embeddings for a vector database, you have to modify its training objective. You have to explicitly train it for representation using contrastive learning or something similar.
But Wang, Isola, and Chung proved that's false.
Completely false. You can get incredibly high-quality semantic representations at inference time from a totally frozen autoregressive model.
Okay, well, semantic richness sounds fantastic on a whiteboard, but if you're building retrieval-augmented generation systems, you need hard numbers.
You do?
So how do we mathematically prove that a mean pooled embedding is objectively more semantic than a last token embedding? How do you even measure semantics in this context?
That is where the centered kernel alignment comes into play. It is a brilliant mathematical tool for comparing the similarity structures of two entirely different representational spaces.
Okay, so how does that work?
Think of CKA like comparing a map of London to a map of Tokyo.
Okay.
The streets, the coordinates, the actual language of the maps are totally different. You can't compare them directly.
Right, they're fundamentally different structures.
But you can look at relationships. You can see if the relative distance between a bank and a grocery store in one city follows a similar clustering logic to the other city.
Oh, I see. So we aren't comparing the raw 4096 dimensional vectors of the LLM directly to the vision model.
No, not at all.
We are comparing the distances between a batch of vectors in the LLM space to the distances between the corresponding vectors in the vision space.
You've got it. That's exactly it. The researchers set this up using paired inputs.
Okay, walk me through an example.
Let's take the vision language domain.
Yeah.
You pair a text caption of an image with the physical image itself. You pass the text to the LLM.
Just a standard prompt.
Actually, to make sure the LLM is really trying to visualize the scene, you use a sensory prompt. Something like, imagine what it would look like to see, followed by the caption.
Meanwhile, you pass the actual image pixels through a reference model. In this paper, they used DynoV2, right?
Yes. DynoV2 is widely accepted as having an incredibly robust, ground truth understanding of visual semantics.
So it's a solid baseline.
Exactly. If the LLM's representation space has a high CKA alignment score with the DynoV2 space, it means the LLM is clustering the text embeddings using the exact same relational logic that the vision model is using to cluster the physical image embeddings.
Wow. So it proves the LLM has captured the true visual semantics of the scene purely from text.
Exactly. And the finding here is striking.
What happens as it generates?
As the model generates its response, token by token, and you average more and more of those generated tokens into your pooled embedding, the CKA alignment score doesn't just go up a little.
It spikes.
It climbs consistently until it eventually surpasses the alignment score of any single token on its own. The aggregate beats the best individual part.
The mean pooled trajectory completely breaks past the ceiling. That's incredible. But we have to address the obvious skeptical counter-argument here.
Right, the math skepticism. Let's hear it.
Let me guess. If you take a bunch of high variance vectors and you average them together, you inherently reduce the variance, you smooth out the noise.
Yes, that's true.
So is this alignment score artificially inflating just because averaging reduces mathematical noise rather than actually capturing deeper meaning? Is it just a statistical illusion?
It is the most logical pushback, and the researchers actually anticipated it. They ran a fascinating ablation study to test exactly that.
Oh, really? What did they do?
First, they injected isotropic noise into the token mean representation.
Isotropic noise? If you aren't familiar, think of isotropic noise as a cloud of perfectly symmetrical, random, mathematical static.
Exactly. If the alignment was just about smoothing out arbitrary variance, adding structured static would behave differently than adding semantic data. But more importantly, they ran a test where they deliberately shuffled the image-text pairings.
Meaning the LLM is processing a caption for a dog, but you are comparing its distance matrix to the DynoV2 embedding of a coffee cup?
Yeah.
You completely break the semantic link.
And when they did that, the alignment improvements vanished entirely. The debiased CKA dropped right back down to baseline.
Wow, so there's no illusion there.
None at all. What this proves is that the pooling operation only works because the average is centering on actual, meaningful semantic structure.
Right. If the pooling was just a variance reduction trick on random vectors, the shuffled kernel wouldn't have completely tanked the alignment.
Exactly. The improvement is strictly mathematically dependent on the semantic correspondence.
Okay, so the math holds up. The signal is real. But if the representation is getting better and better token by token, what exactly is happening inside the model's architecture during the generation process? It isn't just spitting out a flat stream of words.
Far from it. It's executing a complex cognitive process. The paper breaks down the specific alignment trajectory they observed using Qwen 314b.
What does that look like?
Well, if you plot the alignment score over time as the tokens are generated, it is not a flat line, and it's not a smooth, simple curve. It moves through 4 distinct identifiable phases.
Okay, let's break those down. First, you have the generic preamble.
Right. The model is just acknowledging the prompt, outputting things like, okay, let's think about this.
The alignment here is very low, which makes sense because it hasn't actually tackled the problem yet.
Second, you see prompt repetition. The model restates the core entities it needs to focus on. It's essentially loading the variables into its active memory.
Like getting everything organized.
Exactly. Then third, and this is where the magic happens, you have the recall phase. The model starts retrieving relevant knowledge from its internal weights.
And then the fourth phase?
Finally, the fourth phase is the caption-specific response, where it actually outputs the detailed description.
I want to zoom in on that third phase, the recall phase.
Yeah.
The paper highlights an experiment that honestly blew my mind.
Oh, the fourth generation one, yeah.
Yeah. They forced the model to prepend a very specific phrase before answering. They made it generate the tokens. Let me recall what I know.
And what happened?
The moment the model processed those specific tokens, they saw a massive, sharp spike in the alignment score.
It's amazing. Before the model had even output a single word describing the actual visual scene, its internal representation suddenly jumped into alignment with the Dino V2 vision model.
Just by saying, let me recall, it snapped into the right semantic neighborhood.
Exactly, which fundamentally changes how we should view text generation.
How so?
Well, the words being produced are not just an output log for the user to read. They are an interpretable, physical trace of the model's internal computation.
So the text is the computation.
Yes. When the model outputs a thinking token like recall, that token physically shifts the model's internal geometry. It steers the representational state toward the correct semantic space before the answer is even formulated.
The autoregressive nature of the architecture is actually its superpower here. Because every generated token becomes the context for the next step, the model is actively, iteratively building the semantic space it needs to solve the prompt.
Right, it's constructing a scaffolding of meaning.
But knowing that these different phases do different things, that the preamble frames the task, the recall phase activates the knowledge, and the final phase localizes the details, it raises a major question.
How's that?
Do the later tokens just overwrite the earlier ones? Or do they hold totally different pieces of the puzzle? Because, if the final token contains everything, we wouldn't need to pool them.
That is exactly what they wanted to find out. To figure out how these phases interact, the researchers designed what they call the Simplex Experiment.
Okay.
It is arguably the most elegant visualization in the entire paper. They took the sequence of generated tokens and divided it into thirds. The first third, the middle third, and the final third.
And then?
Then they tested convex combinations of these three slices.
Okay, for those listening who might not work with convex geometry every day, picture a triangle. The 3 points or vertices of the triangle represent using 100% of just one slice. The top point is pure early tokens, the bottom left is pure middle tokens, and the bottom right is pure final tokens. A convex combination means testing every possible blend inside that triangle, where the rates of the 3 slices always add up to 100%.
That's a perfect way to visualize it. And the results were incredibly consistent, whether they were testing vision semantics, reasoning tasks, or protein folding.
And what did they see?
The maximum alignment score never occurred at the vertices of the triangle.
Meaning, relying on just one phase of the generation never gave the best result.
Never. The highest alignment was always found in the interior of the triangle. It was always a specific mixture of the different phases of generation.
It's exactly like CMYK color printing.
Oh, that's a cool comparison. How do you mean?
Well, if you want to print a rich, photorealistic image, you can't just use pure cyan or pure magenta. A single token slice is like one of those pure ink cartridges.
Right.
It has strong, vivid information, but it's fundamentally incomplete. The true picture, the deepest semantic representation, only emerges when you mix those tokens in precise proportions.
The tokens contain complementary information, not just redundant information. That complementarity is the core discovery here.
So they each bring something unique to the table.
Yes. The beginning of the generation holds the structural framing of the problem. The middle holds the abstract recall and entity activation. And the end holds the specific localized details of the output.
You need the whole temporal trajectory to capture the model's comprehensive understanding of the concept.
Exactly.
Okay, I am sold on the power of mixing tokens. But here is the practical engineering dilemma. Generating tokens is computationally expensive.
It really is.
It takes time and GPU memory. So if pooling tokens gives us this incredible semantic richness, why don't we just mean pool the input prompt tokens? You pass in a long, detailed prompt, mean pool those embeddings in one quick pass, and skip the generation phase entirely.
That would be the dream, right? And the researchers explicitly tested that shortcut, but it fails.
Oh, really?
Yeah, prompt token representations do not show this same convex mixing improvement. If you run that same simplex experiment, that triangle visualization on the prompt tokens, you don't get that beautiful peak of alignment in the interior.
It doesn't work.
No. The generative phase is uniquely powerful.
But why? Mechanically, inside the transformer, what makes a generated token so profoundly different from a prompt token? They are both just vectors passing through the same attention layers, aren't they?
It comes back to the causal mask and how the context is constructed.
Right.
Prompt tokens are computed under a fixed external context provided by you, the user. The model is just ingesting it.
Right.
But generated tokens are computed under a context that is increasingly being authored by the model itself. The model is effectively talking to itself, shaping its own latent space step by step. It's optimizing its internal state for the specific task at hand.
And they prove this with a truly clever cross-model control experiment, right?
They did. This part is fascinating.
They took the exact text that was generated by Qwen 3.14b, text that we mathematically know possesses this beautiful four-phase structure and high alignment.
Yeah.
But then they took that text and embedded it using two completely different models, OML 3.7b Think and GPTO's 20b.
Right, because if the semantic power was just inherent to the specific words, if the word recall was just a universal magic spell for alignment, then OML 3 should have shown the same alignment spikes.
But it didn't, did
It
it?
absolutely didn't. When OML 3 or GPTOs embedded the text that Qwen 3 generated, the representational phase structure completely vanished. The alignment dynamics flattened out or behaved erratically.
Which proves that these dynamics aren't properties of the raw text string.
Not at all.
The alignment depends entirely on how a specific model processes its own generated tokens. A model's thinking tokens act like a proprietary cognitive language.
I love that phrasing. Proprietary cognitive language.
Yeah, Qwen's internal geometry reacts to Qwen's generations. If you feed that exact same text into Olmo just reads it as flat external text. It doesn't induce the same internal cognitive shifts.
The semantic richness isn't just in the vocabulary. It is in the specific dynamic trajectory through the network's latent space that those words trigger for the specific model that offered them.
So we've been talking entirely about moving horizontally through the model, averaging across the sequence of tokens over time.
Right.
What happens if we move vertically? What if we dig down into the architecture and average across the network layers instead of the tokens?
They check that dimensional axis too, and it turns out the phenomenon is very uniquely tied to the temporal token dimension.
So vertically, it doesn't work.
No. Averaging across the vertical network layers did not improve alignment beyond the performance of the best single layer. You just don't get that synergistic CMYK mixing effect across depth.
Interesting. And there's a fascinating architectural quirk here about where the best representations live, depending on what kind of token you're looking at.
Oh, there is. In prior NLP research, it's been well documented that if you are embedding prompt tokens, the most semantically rich representations usually live in the intermediate layers of the network.
The middle layers do the heavy lifting for external input.
Exactly.
Yeah.
But for generated tokens, this paper found the exact opposite.
Really? Where do they live?
The highest alignment is consistently found at the very late layers, right before the output head.
Yeah.
The representations formed during active generation just fundamentally behave differently than those formed during passive prompt processing.
Wow. So bringing all of this together for the engineers listening to this AI paper podcast breakdown, if you are building a retrieval augmented generation pipeline or a semantic search engine or any system where you need to extract the true deep internal knowledge of an autoregressive model, you have to rethink your extraction strategy.
You really do.
You cannot just grab the last hidden state and assume you have the whole picture. The performance gains of pooling the generated outputs are too massive to ignore. Yes, generating tokens costs compute. But if accuracy and deep semantic matching are your goals, the truth really does lie in the middle of the generated tokens.
It forces us to reevaluate how we extract value from these architectures entirely. And if we connect this to the broader trajectory of AI, it leaves us with a massive paradigm-shifting question.
What's that?
Right now, the entire software industry designs vector databases, evaluation suites, and downstream architectures around the idea that knowledge in an AI is a static vector point in space.
Right. You plot an embedding, it sits there statically, and you measure cosine distance to it. We treat meaning like a single GPS coordinate.
But this MIT paper proves that for autoregressive models, semantic meaning isn't a static point at all. It is distributed. It is a temporal, evolving trajectory across a sequence of generations.
That is wild to think about.
Right. So how might we need to rebuild our entire approach to semantic search? If true understanding in these models inherently unfolds over time, are we currently trying to capture a complex, fluid cognitive motion using a single static photograph?
That is a fascinating engineering problem to solve, and it might just dictate the next generation of vector databases. We are going to leave you with that thought to mull over. We'll catch you on the next breakdown on AI Paper Podcasts.